In the silent reaches of the universe where light bends and time slows, there are engines of gravity so powerful that even the laws of physics strain to describe them. Born from dying stars and ancient collisions, they rule galaxies unseen, shaping everything around them. Tonight we descend into the darkness to trace their origins, witness their fury, and face the most terrifying black holes to exist. He begins at a time when the universe is still hot and crowded with light, a few 100,000 years after the beginning when matter settles, and the first neutral atoms allow darkness to deepen. In this cooling cradle, tiny ripples in density leave faint fingerprints on the cosmic microwave background, and those ripples become the seeds of structure. Gravity takes hold like a patient artisan, tugging on gas and dark matter until clouds fall inward. In that dark nursery, he looks for the first black hole seeds, the compact anchors that will someday rule the hearts of galaxies. He knows the term seed is simple, but it carries a complex set of pathways. One path begins with the first generation of stars, often called the first lights. Born from metal-poor gas, they are heavier than most stars that come after, sometimes hundreds of times the mass of the Sun. Massive stars live fast and die hard. When they run out of the fuel that props them up, gravity wins and the core collapses. Some explode and scatter new elements. Some fall straight through themselves, leaving a black hole of several tens to a few hundred solar masses. These remnants do not shine on their own, but they become bright when they feed. He follows a different path that skips the stellar step entirely. In pockets where gas stays hot and cannot break into smaller clumps, whole clouds may sink without forming stars, creating what astronomers call direct collapse black holes. The result could be a seed already larger than many stellar corpses with a mass of perhaps 100,000 suns. Such a seed would have a head start on becoming a monster. The question is not whether seeds form, but how quickly they grow, and how some become so large so early. He considers the discovered quasars whose light left them more than 13 billion years ago. They are powered by black holes as heavy as billions of suns already mature when the universe is less than a tenth of its current age. To reach that size so fast, either the seed started out large or they found a way to feed at furious rates for long stretches. Observatories become his guides. The Hubble Space Telescope first mapped faint galaxies from the deep past, finding clumps and arcs where gravity from unseen mass magnifies distant light. The Atacama Large Millimeter Array traces cold gas, the raw material of accretion, in young galaxies where stars ignite by the tens of suns each year. The James Webb Space Telescope, with its keen gaze in infrared light, now resolves compact red-laden cores in remote systems, and some of those cores look too dense and too bright to be made by stars alone. He weighs the evidence with care. A bright knot might be a burst of star formation, or it might be a growing seed hiding behind dust. If a spectrum shows broad lines and hot dust heated from the inside out, the case for a young black hole strengthens. If the lines are narrow and the continuum cool, the case softens. Every new spectrum offers a test, and every test adds complexity. Feeding is never smooth. Gas must lose its angular momentum before it can fall in, and that loss requires friction, magnetic fields, and turbulence. The disk that forms around a black hole glows across the spectrum, with the inner rings heating to extremes and bathing their surroundings in high-energy light. That light pushes back on in falling gas, creating a limit to steady feeding. Yet nature finds loopholes. Feeding may happen in bursts with brief periods where inflow outruns radiation pressure. Outflows and winds can clear pathways that later refill. Mergers between galaxies can drive gas to the center and deliver fresh fuel. Each mechanism offers hours to a clock that must add up to billions of suns in mass in a short cosmic time. He holds one puzzle in both hands. If early black holes shine too well, they ionize and heat their neighborhoods, and that heat should stall the inflow. But observations show luminous quasars standing in foggy young universes. Perhaps their energy escapes through funnels carved by jets. Perhaps they flicker, staying bright just long enough to grow, but not long enough to choke themselves. Perhaps many try and fail, and only the lucky lines of sight let us see the survivors. The Chandra X-ray Observatory supplies sharper clues. It finds hard X-rays from compact sources embedded in young galaxies, tiny beacons that mark accretion onto small black holes. Some sources seem too many or too powerful for their host mass, hinting at an era when seeds multiply and compete. The Very Large Telescope and other ground arrays collect spectra that reveal metal, poor gas, and unusual ratios of elements, a chemical fingerprint of early stars and their deaths. Where heavy elements are scarce, cooling is different, and direct collapse becomes more likely. This is where theory meets data and disagrees in interesting ways. Simulations show that radiation from nearby star-forming regions can keep gas hot and stop it from fragmenting, making a direct collapse more feasible, but only if the right intensity and geometry are present. That requirement sounds narrow, yet the sky is large and rare conditions can occur often across vast volumes. He envisions a cosmic archipelago of dark lagoons where gas falls straight toward a waiting horizon. Another thread ties to the Laser Interferometer Gravitational Wave Observatory and its companions that listen for ripples in space-time when compact objects merge. The earliest detections favoured heavy stellar mass black holes heavier than those measured in nearby X-ray binaries. Their existence suggests that low metal environments produce larger remnants. If this holds true at high redshift, the first generations may have seeded the universe with robust building blocks that then merged into intermediate masses. These mergers would ring space with waves too low in frequency for present detectors, but future missions tuned to longer wavelengths promise to hear them from across cosmic history. He keeps a quiet respect for the limits of current instruments. Even with the reach of the James Webb Space Telescope, the frontier is harsh. Light arrives stretched and faint. Distant galaxies look small and their cores blur together with star-forming clumps. Photons carry stories, but their dialect is subtle. He watches observers push techniques to tease out time variability polarizations and line profiles that betray a hidden central engine. A flare that rises and falls over weeks in the galaxy rest frame can be a whisper from a hungry seed. A polarized signal can show scattering off a compact structure. A red wing in a line can hint at gas swirling near a deep potential well. Each clue tightens the net. At the same time, he entertains harder possibilities. Maybe gravity behaves slightly differently in the earliest epochs. Maybe dark matter has interactions that compress gas in unusual ways. Maybe some seeds begin as exotic condensates that collapse under conditions not present today. He does not anchor these ideas as truth. He places them on the table to mark the space where imagination waits for data. The path from a ripple in the early universe to a black hole that can sculpt a galaxy is a sequence of thresholds, and each threshold invites a test. So he stands in that first darkness with instruments in orbit and on mountaintops listening for the faintest beginnings. The seeds are invisible by definition, yet their influence is stamped into the light of the first galaxies, into the chemical patterns of young stars, and into the timing of future waves that will cross the solar system. He ends this layer of the story with a map of possibilities rather than conclusions. The seeds exist, that much the cosmos confirms, but their roots are many, and their growth is a race against bright feedback and scarce time. Somewhere beyond the most distant quasar yet found new seeds are still forming, and their futures remain unwritten. He turns to them next to see how they rise from anonymity into dominion, and what they reveal as they grow. He moves inward from the first seeds to the cities they build, the bright and crowded centers of galaxies, where supermassive black holes sit like hidden mayors behind glowing councils of stars and gas. In the Milky Way, the one at the center goes by the name Sagittarius A, star, and stellar orbits around it trace tight loops that serve as proof of an unseen mass of about 4 million suns. He follows those stars as they whip around the core in periods of years and decades, their paths measured by careful astrometry, with large ground telescopes and adaptive optics. The motions are not guesses, they are clear signatures of a compact heavy presence that no cluster of dim stars can explain. Elsewhere in the cosmos, the same logic unfolds across grander scales. In giant elliptical galaxies, the central black hole is heavier by factors of hundreds or thousands, and its mass appears to correlate with the speed at which stars move in the galactic bulge, a relation that suggests a long dialogue between the black hole and the galaxy it inhabits. He lingers on this link because it reads like a compact contract written in gravity and light. The black hole feeds on gas that sinks to the middle, but when the disk brightens and blows winds, that energy travels outward and can slow the birth of new stars. Over cosmic time feeding and feedback choreograph a balance that fixes the size of the bulge and the mass of the central object. He imagines this exchange as a steady breathing of the galaxy, an inhale of gas that nourishes the core, and an exhale of radiation and particles that sweeps the streets clean. When the core flares into a quasar, the whole galaxy feels the storm. The Chandra X-ray Observatory maps cavities in hot gas that trace the work of radio jets, and the Hubble Space Telescope reveals dust lanes bent by past outbursts. The Atacama Large Millimeter Array tracks cold molecular gas in streaming lanes that lead toward or away from the center, sometimes both at once, as if the galaxy cannot decide whether to eat or to cleanse. He notes that these patterns are not restricted to the loudest objects. Even quiet, supermassive black holes leave fingerprints. In nearby galaxies, faint radio jets carve channels through the interstellar medium, and gentle outflows keep gas warm enough that it resists collapse. The result is a long plateau in star formation, where the city never sleeps but also never erupts. In clusters of galaxies where hundreds of giant systems swim in a sea of hot plasma, the central galaxy often hosts the most forceful feedback. The Chandra X-ray Observatory sees bubbles and ripples, concentric waves that indicate regular injections of energy from the core. Without those injections, the hot gas should cool rapidly and rain down to feed a runaway burst of new stars. Instead, the black hole acts like a caretaker who taps the brakes, heating the atmosphere just enough to avert a crisis. He stands before this population of central giants and feels the scale of their variance. Some weigh millions of suns, some weigh billions. A few extreme cases push toward tens of billions, although those claims carry uncertainties. He thinks about how such masses concentrate into regions smaller than the solar system, and how the gravitational field near the horizon twists time and space. Observers peer into these regions through indirect means. The Event Horizon Telescope stitches radio dishes across the Earth into a globe spanning interferometer, and with that reach it now resolves a ring of emission around the shadow of Sagittarius A star and around the even larger black hole in the galaxy, known as Messier 87. The images show a glowing crescent that brightens where matter moves toward the observer and dims on the far side, a pattern set by motion near the speed of a light and by the lensing of space itself. He reads the ring like a clock face. Its size and thickness tell of the mass and the flow of hot plasma. Its flicker over minutes and hours hints at magnetic knots that tangle and snap. Its polarization traces fields that funnel energy toward jets. The ring does not end the mystery, it sharpens it. If a subtle departure from the expected shape appears, it may point to new physics or to conditions more complex than current models allow. He turns from images to rhythms. The laser interferometer space antenna, still in preparation, promises to listen for long wavelength gravitational waves from binaries of supermassive black holes deep in the distant universe. For now, pulsar timing arrays have begun to sense a background hum that could be the chorus of many such pairs drifting together over cosmic ages. If that hum grows into distinct notes, astronomers will map the rate at which galaxies merge and track how often their central giants find each other and coalesce. He imagines a future where paired monsters broadcast their spiral dance for years, allowing observers to watch gravity do work on the larger stage. Meanwhile, tidal disruption events flash like accidents on the central highway. A passing star wanders too near the horizon, and tidal forces tear it into a stream that lights up as it falls. Telescopes catch these flares in ultraviolet and X-ray light, occasionally in optical light, and sometimes in radio frequencies when a new jet turns on. Each flare provides a mass estimate, a spin constraint, and a snapshot of how quickly the black hole can switch from idle to active. A pattern emerges that is too precise to be entirely random, yet too diverse to be controlled by a single rule. Black hole mass sets the stage, spin sets the choreography, fuel supply sets the tempo. But there are glitches like abrupt dimmings in some active galactic nuclei that defy easy explanation, or sudden narrow line changes that suggest an inner structure rearranged itself on timescales shorter than expected. He is drawn to these outliers because they pressure the models that otherwise run smoothly. If scattered light from a warped inner disk causes the switch, why does the warp rise so fast and settle so slowly? If dust clouds pass in front of the core, why do they sometimes march with a cadence that hints at a hidden, orbiting body? He keeps all options alive while waiting for instruments to test them. The European Space Agency missions, XMM Newton, and the forthcoming Athena extend, and will extend the reach of X-ray spectroscopy, passing iron lines that are broadened and skewed by motion near the inner edge of the disk. Those lines contain a ruler for the spinning frame, a way to measure how the rotation of the whole drags space and influences the position of the innermost stable orbit. He follows these rulers across the population and finds that some monsters spin rapidly enough to tap rotational energy to power jets through a process linked to magnetic fields threading the horizon. Others appear slower, perhaps because of chaotic feeding that flips the disk orientation from episode to episode, cancelling the spin over long time. The diversity points to different life stories. Some grow by steady, prolonged accretion in a fixed direction. Others grow through many mergers and brief meals. The subtlety is that even slow spinners can be dangerous if fresh fuel arrives in quantity. He looks at the wider city once more. Stars near the centre follow orbits sculpted by the past, and there is evidence that nuclear star clusters coexist with supermassive black holes. In many galaxies, a double core that suggests a shared growth. Gas flows along bars and spirals into rings where star formation sparks, and from those rings streams break inward to feed the whole. When a galaxy merger occurs, tidal forces shake loose huge reservoirs of gas, and the core brightens for a while, in a phase that astronomers label a luminous infrared outburst if dust buries the heart, or a quasar if the light escapes. After the blaze, the center may enter a quiet state again, the black hole dim but never absent. He sees in this cycle a portrait of resilience, a system that uses feedback not to destroy but to regulate. Yet the regulation is cold. It cares nothing for individual stars that stray too close, nothing for planets that may wander into harm. Its aim, if aim is the right word, is only equilibrium across scales. The monsters at the centres do not reign by spectacle alone, they reign by setting the conditions for everything else to happen, by keeping the city from collapsing under its own appetite or exploding in a fever of creation. He closes this pass through the central districts with a sense that each galaxy carries a personal accent in its core, a particular balance of spin, mass, fuel and memory. He will return to the most radiant among them, the quasars, to watch how their light can both reveal and conceal the violence that feeds it, and to listen for what their storms say about the rules that govern the rest. He steps into the quasar storm where black holes feed with such vigour that their neighbourhoods glow across the universe and reach us as beacons from deep time. A quasar is an active core powered by a supermassive black hole, a luminous engine where a disk of infalling gas heats to a bright frenzy, and where light can outshine an entire host galaxy. He watches how this light is born from friction in the disk from magnetic fields that braid and break, and from a hot corona that upscatters softer photons into powerful X-rays. The result is a spectrum that spans radio waves to gamma rays, a signature as complex as the weather of a planet, and just as sensitive to small changes. He sees a pattern behind the radiance. The disk swells when fuel arrives, then thins when winds and radiation push back. The outward push sets a ceiling to steady feeding, yet quasars show that nature often climbs past ceilings by becoming variable. The feeding proceeds in bursts of flickering that allows short periods of supergrowth without a long period of self-strangling. He follows this flicker through records of brightness that change over days, months, and years. Some cores dim by a factor of several over a few years, and then revive a behaviour once rare and now recorded across many objects thanks to patient sky surveys. The details depend on mass and spin, and on the structure of the inner disk. When the flow shifts inward or the corona rearranges, the spectrum tilts and winds strengthen or falter. Those winds fascinate him because they carry the storm beyond the horizon's neighbourhood. In ultraviolet light there appear deep absorption troughs that signal outflows moving at thousands to tens of thousands of kilometers per second. The outflows are not smooth shells. They are clumpy layered and sometimes polar, sometimes equatorial. When a clump intercepts the line of sight, the absorption deepens like a passing cloud. When the clump moves aside, the continuum returns. He pictures a sky above the disk striped with streamers of gas that rise and fall, like curtains driven by radiation pressure and by magnetic tension. He notes how different bands of light tell different chapters of the same story. Radio images reveal jets' narrow beams that carry energy and angular momentum far from the center. Some quasars host jets that pierce intergalactic space for hundreds of thousands of light years. In X-rays, the corona speaks, and iron lines twisted by strong gravity sketch the inner orbits. In infrared light, warm dust re-radiates energy absorbed from the disk, hinting at a thick ring or a swollen cocoon around the core. The James Webb Space Telescope adds clarity by resolving the dusty structures in early quasars and by finding red compact nuclei where starlight cannot explain the power. The Chandra X-ray Observatory and XMM Newton weigh in with precise spectra that track how the high-energy tail hardens or softens with changing flow. The Atacama Large Millimeter Array maps cold gas in the host tracing flows that spiral into the center or spray outward after a burst. He gathers these strands into a portrait of feedback that reaches from the event horizon out to the edges of a galaxy. A strong wind can clear the inner kiloparsec, shutting down star formation and setting the bulge on a path toward maturity. A jet can poke holes in surrounding gas-inflating bubbles that lift heavy elements outward and regulate cooling. When many quasars do this across cosmic time, entire populations of galaxies move along a track from blue and growing to red, and settled a demographic shift that echoes the rise and fall of quasar activity itself. Yet the storm hides as much as it reveals. There is the matter of obscured phases where the core is wrapped in dust and gas so thick that only the longest wavelengths and the hardest X-rays escape. He considers an evolutionary path where mergers deliver fuel that buries the center. A buried blaze grows a wind, the wind erodes the cloak, and the quasar emerges as a bright blue point that finally wanes as fuel dwindles. He also considers a path where orientation alone decides. What we see, an axis tilted toward us, reveals the bright core, while an edge view yields a dust-dominated face. Reality may mix both pictures with growth and geometry working together. He weighs the oldest quasars against the clock of the universe and finds them stubborn. Some host black holes with masses of billions of suns when the universe is only a few 100 million years past its first stars. Their light shows high metallicities, a sign that earlier generations of stars lived and died quickly. Their proximity to ionized bubbles in the intergalactic medium suggests that they help carve holes in the cosmic fog during the era when the first ultraviolet sources reionize hydrogen. The sizes of these bubbles become a ruler for how far their influence reaches. He admires the way gravitational lensing occasionally magnifies a distant quasar, splitting it into multiple images, whose brightness flickers independently when intervening stars act as tiny lenses. That microlensing reveals the size of the emitting regions, shrinking the disk to scales comparable to the orbit of a planet, and testing models that would otherwise remain abstract. It also adds complexity because lensing can masquerade as intrinsic variability. The accounting of mass and light must therefore be made with care. He listens for the quasar storm in other languages. Neutrinos almost ghostly sometimes arrive from directions that also host flaring jets, hinting that protons are accelerated to extreme energies within the cores. The Fermi Gamma Ray Space Telescope ties some of these flares to changes in radio jets, but the connection is not simple. Shocks move along the beam, magnetic fields rearrange, and particles switch from one acceleration channel to another. Every event becomes a case study in the country, where electromagnetism and gravity meet under pressure. He remembers that a quasar is not a permanent identity. Hosts switch on and off. A galaxy that was quiet in old images brightens in new ones, and a galaxy that was a textbook active nucleus fades to a whisper. The engines are moody because fuel arrives in streams and clouds, and because inner instabilities can reroute the flow. This moodiness places quasars among the fastest evolving structures in the cosmos when measured in units of their own inner orbits. By tracing the light echoes that bounce off distant dust in a galaxy, when the core changes brightness, observers map the size of the inner structures and turn delays into geometry. He thinks about the line between measurement and mystery. There are spectra with broad lines that suddenly narrow as though the broad line region has thinned or retreated. There are ultraviolet troughs that deepen and then split as if a new stream has peeled away from the disk. There are radio hearts that quiet while large lobes keep glowing, a memory of a jet that was once alive. Each departure from a tidy picture demands a revision. He holds revisions lightly and returns to the heart of the storm. At the rim of the event horizon, gas whirls at a large fraction of the speed of light, and the boundary between matter and radiation becomes porous. Spikes of magnetic pressure can tap the rotational energy of the whole. Twists of field line can launch jets that collimate themselves over immense distances. Into that inner place, photons that would otherwise carry away heat are trapped or diverted so the inner flow can change identity from a thin disk to a puffed hot structure whose light becomes harder. These regime shifts are the hidden seasons of a quasar. They are not weather in a human sense, but the analogy helps regimes linger, then break, then return with different strength. He leaves the storm for now with the sense that its brightest displays are also the moments when the black hole alters the fate of its host the most. The spectacle is therefore a message. It is a sign that matter is reaching a point of decision, that energy is being redistributed across scales, that time at the center is running faster, even as the outer galaxy ambles along. The quasar is terrifying not because it destroys at random, but because it writes rules that other structures must obey, and it writes those rules with light that looks like beauty from far away. He arrives at the rim where theory meets an image, where a telescope the size of Earth is built from many smaller eyes, and where a shadow cut from light itself becomes a measure of gravity's strength. The event horizon telescope is not one instrument, but an orchestra of radio dishes spread across mountain tops and deserts, synchronized by atomic clocks and stitched together by very long baseline interferometry so that the Earth's diameter becomes the lens. He watches as waves at millimeter length slip through clouds of dust and gas carrying whispers from the inner rings of plasma around horizons. The target is a ring of emission, encircling a darkness that is not an object, but a consequence, the region where light paths curve so steeply that most rays fall inward, and only a thin band skates around the hole before escaping. He studies the first success in the galaxy called Messier 87, a giant elliptical far away whose central black hole weighs several billion suns and spans a scale on the sky comparable to a few tens of microarc seconds, an angle so small that it would take many millions of those angles to equal the width of the moon. The image appears as a warm ring with a cooler center bright on one side, where matter spins toward the observer, and dimmer where it recedes, an asymmetry set by motion near the speed of light and by the bending of space itself. He traces the ring's diameter and reads the mass. He looks at its width and reads the temperature and distribution of electrons in the flow. He listens to its flicker over hours and reads turbulence knots and magnetic structures that are born and die at the inner orbit. The image is not a photograph in the ordinary sense, but a reconstruction from sparse samples of spatial frequencies, a delicate inversion that requires careful modelling and cross-checking. Teams blind to one another's methods converge on a shape that holds steadier than any single algorithm, and the ring remains even as the details of brightness shuffle. He finds beauty in the discipline of the process calibrations to correct for weather and gain closure quantities that survive the imperfections of individual stations, time segmentation to track changes that matter for a source with a heartbeat measured in days. He shifts focus to the second target, the black hole in the Milky Way known as Sagittarius, a star, a far lighter object whose inner orbits complete in minutes rather than days. The line of sight to the center crosses clouds that scatter radio waves, blurring fine detail, and the source itself changes so quickly that the Earth's rotation, usually a friend to interferometry, threatens to smear the view. He follows the strategy, short snapshots, careful treatment of the blurring screen-forward modelling of a ring that jitters and brightens on timescales of minutes. The result is a second shadow, consistent with the rules of general relativity, similar in apparent size to expectations for the measured mass and distance. Two very different regimes now offer the same message: gravity near the horizon, behaves as predicted to within the current precision. Yet the images do not end the story. They open passages into deeper questions. He turns to polarization, the twist and orientation of the electric field of the light, which carries a map of magnetic fields in the inner flow. The polarized image of the Messier 87 ring shows patterns like streamlines around a rock in a river, lines that hint at an ordered field capable of launching a jet. That jet has been seen for decades across the spectrum, a narrow spear of energy that punches out of the galaxy and ends in glowing knots far beyond the starlit core. The new polarization maps connect the base of that spear to the ring at the edge of the shadow, suggesting that the engine draws on the black hole's spin through magnetic fields that thread the horizon. He weighs this against models where the disk alone powers the outflow and finds that the data lean toward a hybrid picture where rotation and fields work together. He lingers over the ring size because its diameter serves as a simple ruler of the compact mass and a simple check on any departure from the expected geometry of space-time. If the ring were smaller or larger than predicted for the measured mass suspicion, would fall on alternative ideas of gravity or on exotic matter near the hole. Instead, the size agrees within tens of %, not a trivial tolerance, but a strong constraint already. He imagines future campaigns with more stations, including dishes on high plateaus, and perhaps in space filling the gaps in the sampling and sharpening the ring's edge until finer deviations could be seen. He reflects on the limits baked into the method. The image is made at a single band where the atmosphere allows, and the plasma becomes opaque inside a certain radius, so the ring shows where light last scatters rather than the true horizon. Changes in electron temperature, density, and magnetic structure alter the thickness and brightness around the ring, creating degeneracies that modelers must untangle using other channels of information. He sees observers fold in X-ray flares from the Chandra X-ray Observatory, infrared flashes from ground telescopes, and radio variability from arrays that watch the jet farther out. With timing and correlations, they test whether inner changes send echoes down the jet and whether the same population of electrons produces both the millimeter ring and higher energy flashes through different processes. He takes a step back to consider what terror means in this context. A shadow is the absence of light, but here it is also the presence of a boundary beyond which the idea of escape loses meaning. The shape of the darkness is the silhouette of orbits that no longer exist, a negative space carved by gravity so intense that space itself folds. The knowledge that the image is a calculation made visible does not lessen its weight. Rather, it deepens it, because the calculation is born from equations that have survived every challenge for a century, and now those equations outline a real circle in a real sky. He asks whether the images could ever reveal cracks in the theory. Perhaps a bright quasi-periodic arc skimming the ring could betray a wobble in the innermost orbit not captured by simple models. Perhaps a persistent deviation in ring diameter with viewing angle could hint at an unexpected quadrupole moment, a sign that the central mass is not described by the classic family of solutions. Perhaps polarization patterns could twist in a way that defies all reasonable magnetohydrodynamic flows, forcing a reconsideration of the interplay between matter and space-time. He does not claim these as expectations. He holds them as beacons to steer future observations. He is mindful of an observational irony. The Messier 87 ring is easier to image than the closer Sagittarius A star, because the supermassive giant in the distant galaxy changes slowly while the local one flickers. Yet the flicker is itself a gift because it compresses inner dynamics into humanly accessible times. A flare rises and falls in minutes, and within an observing night one can see patterns shift. Coordinated campaigns therefore attempt to watch across the spectrum at once, catching the ring, the infrared flashes, and the X-ray burst together. In those moments, the black hole is not only an object, it is an event made of many signals. He returns to the human scale of the Enterprise not as sentiment, but as recognition that telescopes built by many hands become a single eye only through trust in shared time and shared method. Atomic clocks at each station mark the arrival of each wave with precision measured in nanoseconds. Hard drives shuttle oceans of bits to central facilities, and correlators search for fringes that prove coherence across half a world. The Earth turns baseline lengths stretch and shrink, and the sky itself becomes part of the instrument. He finds comfort in the patience required because patience is a kind of rigor. It leaves little room for wishful thinking and much room for surprise. He leaves the ring with one more thread in hand. The next generation of observations will attempt to make movies to show the brightness pattern, circling the shadow, and to catch orbiting hotspots that mark magnetic reconnection. If such motion is seen clearly and its speed matches the gravity set by the measured mass, confidence in the whole picture will deepen. If the motion misbehaves, the picture will change, and the change will be instructive. In either outcome, the image will have done its true work not to decorate but to decide. The most terrifying black holes are those that refuse to stay hidden. They let us trace their outline and then dare us to explain why the outline exists and why it holds. He accepts the dare and moves on from the edge of the shadow to the darker questions within. He turns to the darkest outliers, the ones that refuse tidy categories, the ones that bend trend lines until models creak. He begins with supermassive engines that seem too large for their surroundings, black holes whose measured masses outrun the expectations set by the motion of stars in their bulges. In some brightest cluster galaxies, the inferred mass reaches toward tens of billions of suns with light profiles that sag inward and stellar velocities that whisper of an invisible anchor deeper than predicted. He respects the caveats in those measurements, the uncertainties in how starlight spreads, and in how orbits tilt, yet even cautious estimates leave objects that strain the link between a central black hole and its host. If the relation between bulge velocity and black hole mass is a contract negotiated by feeding and feedback, then these extreme citizens look like cases where one party took more than its share. He imagines merger-rich histories where several heavy holes sank to the core and fused, or long eras of privileged feeding, when gas fell inward in a steady stream without interruption. He thinks about the faintest times as well, when the universe is still young and the first brilliant quasars already host black holes whose masses number in billions of suns. Each such quasar is a reminder that fast growth happens whether by direct collapse seeds, by supercritical bursts of accretion that briefly outrun radiation pressure, or by a series of mergers that stack mass faster than simple duty cycles allow. He studies spectra from the most remote quasars and finds metal-rich gas and dust already present signs that stars have lived and died quickly to supply the elements that now glow around the core. The timeline feels compressed, as if the early universe keeps two clocks, one for ordinary structure and one for engines that sprint ahead. He looks for outliers of a different kind, the candidates for supermassive black holes that wander off-center, kicked by the recoil that follows a violent merger, when gravitational waves carry away momentum unevenly. A displaced core would drag its broad line region along like a scarf, and its velocity relative to the host would imprint an offset in spectral lines. Several galaxies offer hints of such shifts, and a few show bright cores with extended tails that might be the path of a recent kick. If confirmed, these refugees would be reminders that even the heaviest anchors can be jostled, that gravity itself can hurl its own makers across starlight. He descends the mass scale to a place where the census has long been puzzling the bridge between stellar mass black holes and the giants at galactic centers. Intermediate mass candidates are rare, yet clusters of stars and stripped dwarf galaxies sometimes harbor compact sources whose behavior suggests masses of thousands to hundreds of thousands of suns. Ultraluminous X-ray sources in nearby spirals flicker with patterns that hint at heavier engines than ordinary stellar remnants, and a few tidal disruption events appear to demand a middleweight interrupter to fit their rise and decay. Radio and optical line widths in a handful of low-mass galaxies point to central objects too heavy for any stellar corpse yet too light to rule a city of stars. He senses there a staircase that once seemed missing beginning to show its steps through fog. The steps might be carved by runaway collisions of stars in young clusters, by the slow merger of many stellar remnants, or by the survival of direct collapse seeds that never found the fuel to become true giants. He listens next to the sky that hums with gravitational waves. The first harvest from the Laser Interferometer Gravitational Wave Observatory and its partners delivered mergers between black holes heavier than expected from the known X-ray binary population, with components of several tens of suns. Those masses pointed to low metallicity birthplaces where stars lose less mass to winds and leave heavier cores. Then came events that pressed into the gap predicted by pair instability, the mass range where a very massive star should unbind itself before it can die quietly into a hole. One famous signal suggested a remnant in the 100 range of suns, an object that belongs squarely in the intermediate class. The N masses and the effective spins inferred from the waves provided more than a census. They offered a diary of how the pair met. Some pairs seemed to form in isolation, their spins roughly aligned, their orbits circular. Others appear born in crowded environments where interactions scramble, orientations producing low or even negative effective spins and eccentric approaches. Among these, a minority may be merger products that merge again, a second generation that climbs the mass ladder into the forbidden gap. He notes that each such case is an outlier only until enough of them accumulate to demand a new category. The detectors march toward greater reach, and future space-based arrays will tune to longer waves, opening ears to the slow unions of heavier pairs across cosmic time. He returns to luminous extremes. A few active nuclei radiate with power so high that a steady disk should be near its standard limit, and yet the observed output suggests surges beyond that ceiling. He considers what supercritical accretion really means, when geometry thins the escaping light along the poles, or when photon trapping carries energy inward rather than out. In such regimes, the mass inflow can exceed the common limit, while the observed light remains within bounds for certain sight lines. The black hole grows quickly, but the sky does not betray the full violence of the meal, except in subtle timing and spectral signatures. He wonders whether some early quasars hid their true appetites this way, and whether a fraction of the present outliers are survivors of that earlier fast lane. He studies cold giants in small towns' central black holes that look too heavy for their faint hosts. In certain compact galaxies with low stellar mass, the core shows signs of a black hole heavy beyond expectation, as if the street lamp at the town square were sized for a capital city. These cases challenge the notion that feedback scales smoothly with mass. Perhaps they are relics of an earlier epoch when fueling was easier, or trophies of a merger that robbed a neighbour and left the victor with an engine too large for its body. He watches for the strangest lights in the night, the transients that defy labels. Some galaxies produce repeating flares that look like partial tidal disruptions, as if a star on a bound orbit gives up a piece of itself at each close pass, dimming and brightening in a cadence that hints at an unseen clock. A handful of nuclei show abrupt changes from bright to faint, by orders of magnitude faster than expected if dust alone moves across the view. Inner structures may flip between states. Disks may tear under the competing pulls of spin and gravity, or magnetic pressure may rewire the flow. Each scenario writes different lines in the spectrum and different delays between bands. Telescopes now learn to coordinate so that when one band wakes, all ears are ready. He pauses over the word terrifying and lets it mean not spectacle, but uncertainty, the way the outliers tell us that patterns we trust are only drafts. The universe keeps exceptions, and in those exceptions it encodes its deeper rules. He considers carefully and without declaration the possibility that some outliers point toward new physics. Perhaps gravity on the smallest horizons or at the earliest times admits slight departures that only the fastest growers reveal. Perhaps dark matter clumps in ways that compress gas more efficiently in certain ancient neighborhoods. Perhaps there are traces of primordial black holes born from density spikes in the first fractions of a second, a population that would have no need of stars to light their path to mass. He does not fold these ideas into conclusions. He sets them as markers for where observation should lean next. Instruments sharpen, surveys deepen, and catalogues grow. With each season of data, objects that once seemed unique find cousins, and families of outliers become sequences that theorists can trace back to shared causes. The darkest outliers are not only extremes, they are trailheads. They do not stand apart to mock our understanding. They stand first along paths that many will later occupy. He finishes this pass with a widened atlas of possibilities and a plan to hunt the bridge class more closely, to search for the missing middle, and to listen for the chords that mergers strike when mass climbs an unexpected stair. He follows the bridge that many maps once left, blank the mass range between stellar corpses and central giants, where black holes of thousands to hundreds of thousands of suns might wait in sparse company. The search begins in places that are small, but crowded the dense hearts of star clusters, where gravity herds thousands of stars into a region only a few light-years across. In such hothouses, repeated close passes rob stars of energy and push the heaviest toward the center, a slow rain that piles mass where collisions become likely. He imagines very young clusters where massive stars still shine and where gas has not yet been blown away. There, runaway mergers can knit several heavy stars into one titan that later collapses almost directly into a black hole, a seed already larger than any simple stellar remnant. He looks to older clusters as well, where many stellar mass black holes drift toward the core and encounter one another in a dance of exchanges and ejections. A fraction of these meetings end in unions, and over long spans, a black hole that begins small can climb in steps fed by companions that arrive with fresh angular momentum and leave as gravitational waves. Observers look for the fingerprints of such a hidden monarch. The Hubble Space Telescope maps the motions of stars near cluster centers with exquisite precision, and a slight rise in speed toward the core can betray an extra mass that light does not show. Yet the sphere of influence is small, often too small for a clear verdict, and mass that hides in a crowd of faint remnants can mimic the pull of a single object. He turns therefore to high-energy light, where accretion tells on itself. Ultra-luminous X-ray sources stand out in nearby galaxies as beacons too bright for most stellar black holes unless they feed in supercritical doses. Some of these lights show transitions between spectral states and timing features that scale in ways suggestive of heavier engines. A few reside not in spirals or in dusty nurseries, but in the outskirts or above the disks near compact star clusters that may be stripped cores of dwarf galaxies. One famous candidate flickers with a period that hints at a companion star on an orbit of days, a rhythm that allows a crude mass estimate pointing to the middleweight class. The Chandra X-ray Observatory and the XMM Newton mission collect the photons that carry these clues, while the Nuclear Spectroscopic Telescope Array extends the spectrum to harder energies where the inner flow leaves a distinct imprint. Sometimes the evidence is indirect but persuasive, a radio counterpart that appears during a transition, a correlation between radio and X-ray power that lands on the so-called fundamental plane of black hole activity at a mass above the stellar range, an optical counterpart whose starlight cannot account for the energy released. He moves from clusters to dwarf galaxies where any central black hole would weigh far less than 1 million suns, and where the host offer a chance to catch the bridge class not merely as a wanderer, but as a ruler, albeit of a small town. Surveys now find narrow-line nuclei in low-mass galaxies, with flickering infrared echoes and soft X-ray cores signatures of accretion scaled down from the giants. In a handful of cases, reverberation mapping measures a light echo delay between the changing continuum and the responding lines, turning time into distance and distance into a rough mass. These masses fall into the thousands to hundreds of thousands of suns numbers that place the objects on the missing steps. He also notes tidal disruption events in small hosts, whose flare shapes and peak temperatures argue for a middleweight interrupter. A stellar mass hole would swallow a star hole without a bright show, and a supermassive hole would tear it more gently and cool the flare. Somewhere in between, the shredding is quick and hot, and the light curve matches that expectation. The laser interferometer, gravitational wave observatory, listens for the lower frequency rings of mergers in this middle range, but present ground-based detectors are tuned to the higher pitch of stellar mass unions. Still, the catalogue hints at the outskirts of the bridge. A few merger remnants enter the 100 suns regime, and hierarchical growth in dense environments could push the next generation higher. The promise glows brightest in the future ear that will fly in space. The laser interferometer, space antenna, will be sensitive to the slow, deep warbles of black holes in the 10,000 to 100,000 suns range spiraling together far away. If such events occur as often as some models predict, the bridge will sing in long notes that last months to years, allowing precise measurement of masses and spins and a map of where the middle class lives. He considers another line of evidence that reaches across wavelengths the scaling of characteristic times. In disks very close to a horizon, the preferred timescales grow with mass, so a quasi-periodic oscillation that repeats every hour in a stellar system might repeat every year in a bridge mass system. Long patience is therefore required, and sky surveys that watch for years become essential. He sees the rise of programs that monitor nuclei night after night, and build time series that are as important as any image. When a middleweight candidate flickers, the shape of its power over time becomes a signature as telling as a spectrum. He balances these successes with caution. Gas geometry can fake a heavy mass. Supercritical accretion can mimic the brightness of a larger engine by collimating light along a polar funnel, and a beamed jet can add power to a core that would otherwise be modest. Dynamical measurements that rely on stellar speeds need careful modelling of orbits and anisotropy. Even gravitational waves will tell a clear story only when many events sketch a distribution that cannot be explained by the tail of the stellar population. He keeps a ledger that lists risks on one side and rewards on the other, and the latter grows as multiple channels support the same claim. He wonders where these middleweights are born. direct collapse in metal-poor gas can produce a seed, in the 100,000 suns range a ready-made bridge that may never grow to become a giant if its host stays small. Runaway stellar collisions in young clusters can leave an object of thousands of suns that later sinks to the center of its galaxy when dynamical friction drags it inward. Repeated mergers in nuclear star clusters can build a middleweight step by step, and tidal stripping during galaxy encounters can leave a naked nucleus that carries its central black hole into a new life as an ultra-compact dwarf. Each path leaves a different context, a different neighborhood of stars and gas. He sees observers using the James Webb Space Telescope to resolve the stellar populations around candidates, to date the bursts of star formation that might coincide with cluster birth, and to weigh the dust that would signal ongoing feeding. He sees radio arrays searching for steady compact cores whose power and size fit engines heavier than stellar remnants, and he sees optical integral field units tracing the motion of stars around the suspected center to catch even a small rise in speed. The bridge once deemed empty now shows planks laid by all these efforts. He feels the tension between the desire for a definitive case and the value of a growing population with mixed signs. A single smoking gun would be satisfying an unambiguous dynamical mass in a nearby system with a clean light curve and a clear spectrum. Yet science often advances by weight of many partial stones, and the arch now holds. He closes his study of the bridge with a return to fear not of spectacle but of implication. If the middle class is real and numerous, then pathways to the largest monsters multiply, and the time required to build 1 billion suns decreases. If the middle class is rare, then the universe achieved its extremes by a narrow route, and the conditions that allowed it may have been precious and fleeting. Either result sharpens the larger story. He steps onward from the bridge toward the machines that feed these engines, the disks and the spirals and the magnetic fields that turn falling gas into light and wind, where the next layer of terror resides in the quiet arithmetic of energy, converted at the threshold of no return. He turns toward the last acts of stars and watches how gravity claims what fusion can no longer hold, how the embers of a life collapse into a compact remnant that can sleep for ages or flare awake in hunger. A massive star begins with a furnace in its core that fuses light elements into heavier ones, layer by layer building an onion of burning shells. Each layer buys time, but each layer ends sooner than the one before, until the core reaches iron and can no longer extract energy by fusion. When that moment arrives, the star loses its balance in a breath, and the core falls. In a heartbeat, the density climbs to that of a nucleus, and more the inner regions rebound, and a shock wave tries to fight its way out through the infalling mantle. Neutrinos flood from the crushed interior and carry away a vast sum of energy, some of which helps revive the shock. The result is a core collapse supernova that for a brief time can outshine the entire host galaxy. What remains at the center depends on the mass and on how the shock does its work. For some stars, the compact remnant is a neutron star, a city-sized sphere of degenerate matter whose magnetic field and spin can power pulsars. For heavier cores, or for explosions that stall, the remnant is a black hole, a gravitational well with an event horizon as a boundary where escape ceases to be a meaningful idea. He studies the line between these outcomes and finds it blurred by rotation, metallicity, and binarity. In metal-poor environments, stars lose less mass. To winds keep heavier cores and leave black holes more often. The Laser Interferometer, Gravitational Wave Observatory and its partners have already heard the mergers of such heavy stellar mass black holes with component masses of several tens of suns, a sign that low metal birthplaces are common in the ancient universe, and still present today in certain dwarf galaxies. At even higher mass, a different fate intrudes pair. Instability can create a runaway that unbinds the star before a black hole can form, carving a gap in the expected mass spectrum. Yet the gap does not stay empty, because hierarchical mergers in dense clusters can climb across it. He shifts from solitary deaths to partnerships where a black hole awakens through accretion. In a binary, if the companion expands and fills its Roch-Lobe, gas spills through an inner point and forms a disk around the compact object. Friction and turbulence heat the disk and X-rays pour out, marking an X-ray binary. Some systems feed through winds instead, with matter stripped from an O-type or B-type star and captured in a stochastic flow. The light that emerges carries signatures of the inner regime. In soft states, the disk radiates like a multicolored black body, with temperatures of millions of degrees near the innermost stable orbit. In hard states, a hot, optically thin corona upscatters soft photons into a power law tail, and compact steady jets appear in radio light. Transitions between states come with changes in timing. Quasi-periodic oscillations rise and fade. Broadband noise shifts and ion emission lines broaden and skew as they reflect off the inner disk under the pull of strong gravity. The Chandra X-ray Observatory and the XMM Newton mission resolve these lines and measure how close the disk can approach a clue to the spin of the black hole. The Nuclear Spectroscopic Telescope Array extends the reach to higher energies, where the coronal signature grows. The Neutron Star Interior Composition Explorer watches with fine time resolution, catching brief hints of oscillations that may map the epicycles of gas near the brink. In the radio arrays, pick up jets in microquasars, scaled versions of the beams seen in galaxy cores, and track knots that move with apparent superluminal speeds due to projection and near-light motion. He watches one more path to awakening. A black hole can be born with a kick from an asymmetric explosion, and that kick sometimes alters or destroys the binary. When the pair remains bound, the eccentric orbit can drive bursts of accretion near periastron, creating a pattern of outbursts as regular as a clock. When the kick ejects the pair from a young cluster, the system travels into the field and lights up far from any nursery a beacon of death wandering the galaxy. Optical monitoring from surveys now finds candidates by their cluttered light curves and follow up with large telescopes supported by the European Southern Observatory, disentangles contributions from the donor star, the hot spot, where gas meets the disk and the irradiated face of the companion. He notes how black holes and neutron stars can masquerade as one another in certain states. A thermonuclear burst proves a neutron star, but the absence of a burst does not prove a hole. High-frequency oscillations and spectral cutoffs provide clues, but demand cautious interpretation. Polarization of X-rays, now accessible to a new generation of instruments, carries the imprint of magnetic geometry and scattering, yet it also requires careful foreknowledge of geometry and orientation. He listens to how the energy flows and sees that even in these stellar-scale engines, the same physics of inflow-outflow and feedback applies as in galactic cores. Jets carry away angular momentum and help determine whether the inner disk can reach the innermost orbit. Winds from the disk can remove a significant fraction of the infalling matter, lowering the efficiency of growth while raising the influence on the environment. Radiation from the inner regions heats and ionizes the outer disk, and the donor's atmosphere altering the very fuel that sustains the engine. He considers gamma-ray bursts that flash when the largest stars die or when compact objects merge. In the collapsar picture, a very massive, rapidly rotating star collapses into a black hole that promptly launches a jet. The jet tunnels through the star and erupts as a brief, hard burst of gamma rays followed by an afterglow across the spectrum. Space-based telescopes such as the Fermi Gamma Ray Space Telescope and the Neil Gehrels Swift Observatory have watched these events for years, and the pattern of prompt spikes, spectral lags and broken power law afterglows tells of shocks and magnetic reconnection in ultra-relativistic flows. Some bursts mark neutron star mergers instead, and when that happens, the Laser Interferometer Gravitational Wave Observatory and Virgo can hear the inspiral, allowing a direct association between gravitational waves and high-energy light. In both cases, a fast-spinning black hole likely sits at the center, and the aftermath enriches the surroundings with heavy elements created in the ejecta. He looks at the local census of stellar mass black holes and sees that our sample is incomplete, shaped by selection effects that favor brighter creters. Many black holes may spend most of their time in quiescence, dim and detectable only by the tug they exert on an unseen companion. Gaia astrometry, with its precise maps of stellar motion, begins to reveal candidates by tiny wobbles, and spectroscopic campaigns confirm some by Doppler shifts that trace invisible mass. The list grows slowly, but as it grows, it refines the distribution of masses and spins a distribution that we'll need to compare against the mergers heard in gravitational waves. He weighs the fear that comes with the knowledge that black holes can form within a single lifetime of a massive star. A star born in a nearby spiral could expire and leave a remnant that lights as an X-ray binary within the time span of human history. Yet he finds the terror more in the arithmetic than in the spectacle. A black hole converts a significant fraction of the rest mass of the infalling gas into radiation far more efficient than nuclear fusion. A small mass can therefore unleash a storm of energy that sculpts its neighborhood, and that efficiency repeats across scales. The same conversion that governs quasars governs microquasars. The same patterns of states and jets echo at different masses with timescales stretched by the weight of the central object. He gathers the threads into the story's next step. Stellar farewells create the initial conditions, but the immortal engines that follow are defined by how they feed. Disks, coronas, winds, and jets set the cadence of growth and the reach of influence. The missions that watch in X-rays, gamma rays, radio, and optical track, that cadence, and the detectors that listen to space-time itself translate catastrophes into music. The lessons learned from the small inform the understanding of the large, and outliers at the stellar scale foreshadow mysteries that await at the edge of supermassive horizons. He turns now to events that occur when stars stray too near the giants at galactic centers, where the boundary between a controlled meal and a violent shredding becomes a laboratory for gravity at its most immediate. He stands at the boundary between a controlled meal and a violent shredding, and watches a star stray too close to a dormant giant. Gravity stretches the star into a teardrop, then into a thin ribbon, then into beads along a stream, as tides overcome the strength that held the star together. This is a tidal disruption event, and it begins with an orbit that grazes a limit, where self-gravity loses the contest to the black hole's tidal field. About half of the torn mass swings away on open paths and escapes, while the rest falls onto elongated trajectories that loop back toward the center. Where those returning streams collide, shocks heat the gas, and the chaotic flow begins to circularize into a disk that can feed the black hole. He notes that the light does not always rise from a thin disk beside the horizon. Sometimes the first glow comes from those collisions themselves, far from the point of no return, where streams slam together at speeds that are a large fraction of the speed of light and fling matter into a thick, turbulent structure that reprocesses high-energy photons into ultraviolet and optical light. The flare brightens over days or weeks, then decays over months, often following a steady decline that hints at the rate at which stellar debris returns to pericenter. In X-rays, a hot source may appear first, a searing inner engine wrapped in a thinner cloak. In optical and ultraviolet light, a cooler, broader photosphere often dominates when winds puff the atmosphere. He listens across the spectrum as observatories respond. The Neil Gehrels Swift Observatory catches the early rise and traces the ultraviolet arc. The Chandra X-ray Observatory, an XMM Newton, pry open the high-energy band to reveal whether a compact inner disk has formed. The Nuclear Spectroscopic Telescope Array extends the lens to harder energies when a corona hardens the spectrum. Ground-based surveys add discovery after discovery by watching the sky with machine cadence and follow-up spectroscopy pins down redshifts and line shapes. The lines tell how deep the cut went. Hydrogen and helium features wax and wane, sometimes skewed and double-peaked, as if the emitting gas skims a rotating disk, sometimes round and narrow, as if it flows in a wind. The ratio between helium and hydrogen may tilt toward helium if the star lost its hydrogen envelope before the encounter, or if ionization selects layers with different composition. He sees a class where dust nearby glows as it absorbs the flare and re-radiates in infrared, a delayed echo that maps the geography around the black hole. In radio telescopes pick up shock waves that plow into the interstellar medium when the event drives an outflow, and the timing of the radio peak says how strong and how fast that outflow was. In rare cases, a jet lights up and points partly toward us, and the flare then roars in X-rays and radio with a ferocity that rivals a small quasar. Those jetted disruptions look like microcosms of long-lived active nuclei, except that the engine spins up from silence to storm in days. He turns to the simple rule that stars are not all equal in their fate. For a black hole above roughly 100 million suns, the tidal radius lies inside the event horizon for a solar-type star, and the star would vanish with little outward show. Smaller holes more easily shred a main sequence star in view of the cosmos. White dwarfs offer a different case. An intermediate mass black hole can tear a white dwarf near its surface. Compression and shocks can ignite runaway thermonuclear burning in the debris, and the flare can carry chemical signs of that sudden alchemy. A few enigmatic transients in small galaxies show calcium-heavy or oxygen-heavy spectra and fast timescales that hint at this path a signpost toward the very middleweights whose census remains incomplete. He adds another corridor where the star survives a partial disruption that strips only the outer layers and leaves a core on an elongated orbit. Each close pass then removes more mass, and the galaxy flickers in a cadence set by the orbital period. This repetition is a clock that reveals the shape of space-time near the center. General relativity bends the orbit so that the returning stream meets the outgoing stream at different places, altering the shock geometry from pass to pass, and the pattern of flares becomes a probe of precession. He considers the puzzle of circularization. If space-time precession is strong streams intersect quickly, and energy is dissipated early making a bright hot flare. If precession is weak or the impact parameter is small, streams may miss for a while, and the light may rise more slowly or emerge in softer bands. Observations show both behaviors, suggesting that tidal disruptions come in families distinguished by geometry and black hole spin. He weighs the role of winds as the inner engine tries to feed near its natural ceiling. When inflow outpaces the ability of radiation to escape, photons are trapped and carried inward, and mass is driven out along polar funnels. The wind veils the hot center and turns hard light into softer colors, explaining why many tidal disruptions look cooler than a bare disk would predict. As the outflow thins, X-rays grow stronger or appear late after a long delay, When the disk finally clears a pathway to our line of sight, he watches the host galaxies and sees a preference that is more than coincidence. Many events occur in galaxies with quiet star formation and with central populations that include a surplus of rare compact stars. Stellar dynamics in such nuclei may send stars into loss, cone orbits more efficiently, and recent mergers that upset the gravity field may refill the loss cone, boosting the rate. The rate itself is low per galaxy per century, yet the universe supplies many galaxies, and wide field surveys now catch several each year, turning the once exotic into a workflow. He notes the uses that stretch beyond the flare. By modelling the shape of the early rise and the temperature evolution, one can bound the mass of the black hole and sometimes its spin. Spin alters how close matter can orbit stably, and a rapidly rotating hole allows a smaller innermost orbit and hotter emission. Polarization measurements add another handle showing whether the light has scattered in a wind with a preferred geometry or whether it comes directly from a disk. Late-time radio reveals the energy of the outflow long after the thermal light fades. Infrared echoes measure the dust map and the opening angle of any funnel. Even the absence of a particular band becomes informative. A bright optical event with no X-rays points towards strong reprocessing. A hard X-ray burst with minimal optical may mark a jet. He keeps an eye on anomalies that refuse to fit. A handful of disruptions dim faster than expected, as if the debris were swallowed whole in a gulp, or as if the circularization failed. Others show plateaus and rebrightenings that argue for shocks at large radii, or for a delayed stream that finds the main flow late. A few present narrow high ionization lines that switch on and off as if an inner lamp strobed. He places these oddities on a map whose axes are black hole mass spin impact parameter and viewing angle, and he sees regions of that map still blank. He allows himself a measured speculation about deeper tests. If spectral lines from iron fluoresce near the inner edge and carry the signature of strong gravity, their shape could test the geometry around the hole. If a persistent quasi-periodic signal appears and matches an orbital time at a specific radius, it could measure mass and spin without a touch. If future detectors listen to low-frequency gravitational waves from a star on a tight gradual in-spiral under extreme mass ratio, the combined light and waves could sketch a space-time portrait. He closes this pass with a recognition of why these events qualify as terrifying. It is not only the violence done to a star, it is the way a black hole that was dim and dormant for ages can awaken in an instant, rearrange the center of its galaxy for a season, and then return to quiet with a changed memory. It is the way the flare serves as a flare, in another sense a signal that marks a hidden mass, carves a corner on the atlas of intermediate engines, and lights a path to the mechanics of feeding. From this stage he walks forward to the straightest signatures of expulsion, the beams that black holes launch when conditions align, thin columns that carry influence across tens of thousands of light years and inscribe the will of the horizon on the larger sky. He follows the narrow beams that black holes launch when magnetic fields thread the inner flow and rotation twists space into a nozzle, and he watches how these jets become the straightest handwriting in the sky. Near the event horizon, charged particles surf magnetic lines that are anchored in the disk and more crucially in the spinning fabric around the hole. Rotation drags those lines and winds them into a helix storing energy, intention, and pressure that can be released as a collimated outflow. The process begins within a few gravitational radii where orbits crowd and time dilates, yet the consequence stretches for tens of thousands of light years, and sometimes for millions, carving cavities in galaxy halos and lighting distant knots as moving shocks. He pictures the inner engine as a partnership between gravity and magnetism. The disk brings field inward. The spinning hole offers rotational energy. The pair together lift plasma from the poles and accelerate it to speeds that approach the speed of light. The outflow starts as a magnetically dominated wind, tight and cold, in the sense of low random motion, and then converts field energy into particle energy as distance increases, building a beam with a fast spine and a slower sheath. The sheath interacts with the surrounding medium and helps confine the spine, a natural collimator that keeps the stream straight across enormous scales. He steps outward to what telescopes witness. In radio images, jets appear as strings of bright knots marching away from the core. The knots are not discrete bullets, but waves and shocks where pressure changes compress the plasma and brighten it. Very long baseline arrays watch these knots shift from one epoch to the next and measure apparent speeds that exceed the speed of light, a projection effect that occurs when a pattern moves almost at light speed along a direction close to our line of sight. The illusion is a reminder that the true speed sits just shy of the ultimate limit, and that the jet lives where relativity is not a correction, but the rule. In optical and X-ray light, some knots continue to shine, meaning that particles are accelerated not just near the core but repeatedly along the path. Magnetic reconnection, where field lines snap and rejoin, can heat and energize particles in localized bursts. Oblique shocks can do the same. Polarization maps reveal ordered fields that twist and untwist, sometimes aligning with the jet, sometimes crossing it, a tapestry that changes with each disturbance. He traces the jet to its end, where it meets the surrounding gas and forms a termination shock. Beyond that shock, broad lobes inflate like balloons and glow in radio light, their edges flattened where they press against the medium. In clusters of galaxies, the X-ray view shows cavities cut into the hot atmosphere, and ripples ripple outward like the rings of a pond, signatures of repeated outbursts over millions of years. The energy pumped into those cavities prevents gas from cooling too quickly and raining down to form stars. Thus, a thin beam launched at a horizon controls the climate of a giant city of stars, a breathtaking leverage of scale. He turns to the question of composition. Are the beams made primarily of electrons and their antimatter twins, or do they carry a significant fraction of heavy particles that add inertia and change how shocks work? Observations hint at both, with some sources favoring light pairs near the base, and mixed content farther out where mass loading from the environment grows. Neutrino detections from directions that host flaring jets suggest that in at least some cases protons are accelerated to extreme energies and collide to produce pions that decay into neutrinos. The arrival of a high-energy neutrino within days of a gamma-ray surge in a known blazar is not yet a rule, but it is a strong hint that jets play a role in the highest energy particles ever recorded to Earth. He listens to the light curves of jetted cores and hears a symphony of timescales. There are minute-scale flashes in gamma rays that demand an origin in a very small region, perhaps a moving zone within the jet, where reconnection suddenly releases magnetic energy. There are day-scale swings that trace shocks crossing a standing recollimation point where pressure squeezes the beam. There are year-scale trends as the jet precesses or as the accretion flow changes its state. In some systems that harbour two black holes, precession and interaction could imprint slow modulations that ride on faster weather. He sees how microquasars in our galaxy echo the same patterns, with clocks sped up by their lower mass switching from a hard state with a steady compact jet to a soft state with a quenched jet as the inner flow rearranges. The parallel confirms that a single set of physical rules governs engines across a vast mass range. He dwells on the base of the jet the region millimeter telescopes are beginning to resolve. Polarization at the ring of emission around the shadow in the great elliptical galaxy shows a structure consistent with a magnetic field that can launch and control an outflow. The alignment between the bright crescent and the direction of the larger scale jet hints that the geometry is not an accident but a coherent structure spanning orders of magnitude in radius. If future imaging can track a rotating pattern that marches around the ring and then see a delayed response in the jet farther out, observers will have stitched cause and effect across space and time. He considers the jet's impact on its host in quieter galaxies, where the core is not a quasar but still lives. Gentle low-power jets percolate through the interstellar medium, shocking clouds and stirring turbulence that can both suppress and trigger star formation depending on local density and pressure. In some galaxies, narrow cones of warm ionized gas outline paths where the jet has bored escape routes, and along those paths young stars appear footprints of triggered collapse in compressed shells. Thus jets do not merely subtract fuel, they can also seed new structure. He looks at misbehavior and finds it instructive. Some jets bend sharply, either because they encounter dense clouds, or because the launching direction changes as the inner disk wobbles under the torque of a tilted spin. Some jets show limb brightening where the edges glow more than the center, consistent with a slower sheath that radiates more efficiently than the fast spine. Some display sudden pauses with the inner core dim while distant lobes keep glowing, a fossil record of past activity. In a few dramatic cases, a new jet turns on at a fresh angle, after a merger producing an X shape in radio lobes that marks a change of axis. He keeps a cautious eye on claims that jets violate energy budgets. When geometry beams light toward us, a modest power can look immense. Careful accounting with multi-wavelength data often resolves tension. Still, there are bursts whose brevity and brightness push models toward very efficient reconnection, or toward moving mirrors within the flow that amplify radiation by reflection. Each extreme event becomes a test of how quickly magnetic energy can be turned into light. He returns to terror and defines it here as the strictness of the jet. It draws a line across space and says that along this line momentum will be carried and boundaries will be set. It says that a horizon can reach into a cluster and decide how much gas becomes stars. It says that a rotating whole can shed its spin over eons by feeding the sky with the beams. The straightness is an argument. The lobes are the proof. He ends by listening for a deeper tone that jets cannot carry alone. When black holes meet and merge, space itself rings, and those gravitational chords announce the birth of a new spin and a new chance for an axis to tilt. The next layer of the story therefore shifts from outflow to collision, from lines drawn outward to waves sent everywhere, and the instruments that hear those waves will tell whether the engines that launch the straightest beams are themselves born in quiet or in violence. He listens for the deepest music the cosmos allows, a sound made not of air but of geometry itself. When two compact masses draw close, they do not merely circle. They need space-time, and the fabric replies with waves that run outward at the speed of light. Those waves carry a biography in their shape. The soft rise in pitch during the long approach tells the masses and the distance. The sudden leap into a bright crest tells the last orbits and the moment of contact. The fading ring down tells the spin of the newborn horizon and how quickly it swallows its own vibrations. Instruments on Earth have learned to hear this faint song by comparing the lengths of laser-lit arms with a precision finer than the width of a proton. The Laser Interferometer, gravitational wave observatory in the United States, lengthens its arms through vacuum tunnels and bounces light between mirrors so still that even thermal breath seems loud. The Virgo Interferometer in Europe adds a second ear. The Kamiaka gravitational wave detector in Japan adds a third carved into rock to dodge the quiver of the wind. With 3 ears, the sky can be triangulated and the source can be placed upon the dome with enough accuracy to summon telescopes of light. He remembers the first rush of events when the catalogue began to fill with unions of black holes heavier than those long studied in X-ray binaries. The components often weighed several tens of suns, and their spins hinted at history. Some pairs possessed rotations roughly aligned with the orbit, a sign that they may have evolved together from a wide stellar binary that shrank. Others revealed spins that cancelled or even opposed the orbit, a sign that they may have met as strangers inside a crowded star cluster where chance and exchange write the rules. A few carried remnants heavy enough to enter the range where pair instability in stars should create a gap, and that fact whispered that some black holes are children of previous mergers, second-generation stones added to a growing cairn. He listens not only to the approach but to the ring down. After the union, the space-time around the new horizon vibrates in a set of favoured modes. Each mode is a note with a pitch, and a decay time defined by the mass and the spin of the final object. If more than one overtone is measured, the notes become a test that goes beyond fit and toward identity. The notes should agree with the simple family of solutions that govern rotating black holes in general relativity. A disagreement would force a reckoning with the theory that has guided a century of gravity. So far the notes match within the strength allowed by the data, yet the very attempt to hear separate tones is a promise that sensitivity is climbing toward a spectroscopy of horizons. He shifts from single events to the choir of many. A background of overlapping waves rises from the sum of countless pairs scattered across cosmic history. Networks that time the steady flashes of millisecond pulsars now feel a slow swell in the timing residuals, a possible footprint of that cosmic hum. If the signal stands as a background born of pairs of supermassive black holes drawing together during the lives of merging galaxies, then the amplitude and colour of the hum will measure how often galaxies meet, how quickly their central giants lose energy to stars and gas, and how they make the final approach where dynamical friction fails and gravitational radiation takes over. He imagines a future instrument in space, the Laser Interferometer Space Antenna. 3 spacecraft forming a huge triangle that follows the Earth around the Sun. Its arms will be millions of kilometers long, and it will listen to waves far slower than those on Earth. In that band, the approach of pairs of black holes with masses of hundreds of thousands to millions of suns will last months or years. Their tones will drift slowly upward as the spiral tightens, and the signals will be clear enough to measure mass and spin with exquisite precision. Some sources will be heard far in advance of their union, allowing telescopes to watch the changing light from the host galaxy before, during and after the collision. He returns to the rare moments when waves and light have already met. When 2 neutron stars collided in a nearby galaxy, the wave signal announced the masses and the orbit, and within hours telescopes saw a fading spark that swept from blue to red as heavy elements formed in the ejector. The association proved that such mergers forge gold, platinum and other R-process elements, and it offered a lesson for black holes as well, because similar campaigns now chase the more elusive light from black hole unions. Most black hole mergers do not light the sky. They happen in vacuum with little gas to heat. Yet a minority may occur within a disk around a supermassive black hole, or inside a dense gas-rich nuclear cluster where shocked gas could flash. Claims of flares coincident with waves have been suggestive but not decisive, and he holds them as stimuli for closer coordination. Even a single convincing association would reveal the immediate neighbourhood where some pairs grow. He studies what the catalogue of waves says about the population of stellar mass black holes. The mass distribution is broad, with a rise towards several tens of suns, and hints of structure that reflect how metal content changes across time and place. Low metal environments yield heavier remnants because winds strip less mass from massive stars. High metal environments yield lighter remnants. Spin distributions speak of history as well. If many spins are small or misaligned chaotic accretion, and dynamical pairing in clusters become likely contributors. If a subpopulation shows high aligned spins, common envelope evolution in binaries becomes a stronger channel. Each new season adds events and sharpens the inference, turning anecdote into measurement. He gives a careful glance to eccentricity, that subtle deviation from a perfect circle. Most pairs that formed in isolation will have lost their eccentricity by the time they enter the band accessible to ground instruments. But pairs born in tight encounters within clusters can retain a measurable eccentricity at the moment of detection. A few signals already show hints of eccentric tracks, and future detectors with broader bandwidth and lower noise will make such signatures clear. The presence or absence of eccentric events will tell how often black holes meet in dense environments, where three-body exchanges and resonant scatterings are common. He thinks about the limits of the current ears. On Earth, seismic murmur and thermal motion impose a wall at low frequencies, so the approach of supermassive pairs is too slow to hear from the ground. At high frequencies, the small mirrors and finite laser power set a ceiling. Within those bounds, the global network has done astonishing work, yet he knows that widening the band is the key to hearing the full story. That is why the space triangle matters, and that is why pulsar clocks matter, because together they span from the slow music of galaxy centers to the quick staccato of stellar deaths. He entertains the possibility of small deviations from the expected waveform. Could a dark boson cloud grown by superradiance around a spinning black hole imprint a cycle as it drains energy from the spin? Could alternative polarizations exist that general relativity forbids leaving faint but detectable fingerprints in the response pattern across a network of detectors? Could the final ring-down hide a subtle echo if the horizon were replaced by an exotic surface? He does not promote these ideas to truth. He keeps them as compass points that guide how to search. Null results will be as valuable as detections because they will stiffen the framework of gravity where it has never been tested before. He narrows back to terror, and again it is not spectacle, but strictness. Gravitational waves are unforgiving witnesses. They are not filtered by dust or gas. They do not scatter in the interstellar medium. They report directly on the motion of mass, and they audit our accounts of how black holes are born, how they meet, and how they settle. When a signal arrives, the numbers follow. The distance unfolds from the amplitude. The masses unfold from the chirp. The spin unfolds from the ring. The recoil that the remnant receives from asymmetric emission unfolds from a slight bias in the waves, and that recoil may be strong enough to shove a newborn black hole away from the center that made it. The chords of space-time tell all of this without the mediation of light. He closes this layer with a glance forward to a time when a spiral of a small compact object into a supermassive black hole will be heard for many months by the instrument in space. Each turn of that extreme mass ratio in spiral will map a different latitude and radius in the curved geometry, writing a cartography of the region just outside the horizon. If the map matches the expected shape, confidence in the theory will settle deeper than image or spectrum can give. If the map deviates, new physics will have announced itself not with a flash but with a steady song. He listens and he prepares to follow that song from waves to the rotating frames that shape them, where spin drags space and time until even the stage begins to turn. He turns to rotation and watches how a spinning black hole drags the stage beneath every actor, how the fabric of space and time twists so that even empty orbits feel a torque. In general relativity, a rotating mass does not merely sit and pull. It whirls the nearby coordinates a lens-thurring drift that forces any gyroscope or ring of gas to precess. Near a horizon, this frame dragging becomes extreme, so that a particle that wishes to hover must borrow the rotation just to stand still relative to distant stars. He begins with the quiet ruler that rotation provides the radius of the innermost stable circular orbit. For a non-spinning hole, that last safe ring lies at a fixed multiple of the gravitational radius. For a rapidly spinning hole with a prograde disk, the innermost orbit slides inward by a factor of several, allowing matter to plunge from closer in and release more energy as light. A retrograde disk is shoved outward and loses efficiency. This simple geometry turns spin into an engine rating. When disks reach the innermost ring, the radiative efficiency can double compared with the quiet case, and the color of the spectrum shifts toward harder light. He follows how observatories read this imprint. The Chandra X-ray Observatory, the European mission XMM Newton, and the Nuclear Spectroscopic Telescope Array resolve ion emission that has been broadened and bent by strong gravity. The degree of skew and the reach of the red wing announce how near the disk approaches the center, and therefore how fast the hole spins and in which sense the gas turns. In stellar systems, the shape of the thermal continuum itself can be used to infer the inner radius, and long campaigns map how the inferred radius holds steady over time when the source sits in a stable state. Polarization adds a second key. The imaging X-ray. Polarimetry Explorer measures the angle and degree of polarization across energy, and the way those angles swirl with energy and time reveals the tilt and thickness of the inner flow and the direction of the twisting frame. He studies the Bardeen-Peterson effect, the compromise that a misaligned disk and a dragging frame strike with one another. The inner rings feel strong frame dragging and try to align with the equator of the spin, while the outer rings remain loyal to their original plane set by the donor star or the galaxy at large. Between these regions, a warp forms and communicates through sound waves and viscosity, bending the disk into a gentle S. In some circumstances, if the disk is thin and the torque strong, the inner alignment happens quickly, and the jet points along the spin axis. In others, if the disk is thick or the inflow chaotic, the alignment is partial, intermittent, or slow, and the launching direction wanders. He follows that wandering into observation. In microquasars, precessing jets carve corkscrew tracks in radio maps, and quasi-periodic oscillations in X-ray light appear at frequencies that match expected precession periods for tilted inner flows. In active galactic nuclei, year-scale swings in polarization angle and long-term changes in jet position hint at a similar dance carried out on a slower clock. He examines a complementary picture where magnetic fields dominate the inner stage. When enough magnetic flux piles up near the horizon, pressure from the field pushes back on the inflow, and the disk enters a magnetically arrested state. In that state, rotation can be tapped more efficiently, and jets can be brighter and more stable. The polarized ring around the shadow in the giant elliptical galaxy that hosts a famous jet shows a pattern consistent with such an ordered, powerful field. If rotation and fields together set the efficiency, then the highest power jets likely prefer rapidly spinning holes that have hoarded magnetic flux to the point of near stasis, a condition that simulations reproduce and that observations increasingly support. He considers how spin is acquired. A black hole born from a star inherits the angular momentum of its core, modified by any asymmetric flows during collapse. Subsequent accretion can either boost or erode that spin. If the inflow keeps a common direction for long stretches, the spin climbs toward a high fraction of the maximum, and the innermost orbit moves inward. If the inflow arrives in many short episodes with random tilts, the increments cancel, and the spin stays modest. Mergers between black holes add a different path, sometimes producing a remnant that spins rapidly, sometimes producing a slow spinner, depending on the masses and orientations. He knows that populations tell stories, in bright, steady quasars that appear to have fed for a long time in a fixed orientation. Measurements lean toward rapid rotation. In lower mass active nuclei that flicker and change, class spin estimates scatter a sign that feeding has been less coherent. In X-ray binaries, some black holes appear to spin quickly, perhaps because the donor star poured mass for millions of years in one direction, while others spin more slowly, perhaps because their companions never supplied a long, well-aimed stream. He watches rotation bend not only the orbits but the timing. High-frequency, quasi-periodic oscillations observed in stellar mass systems cluster at values that match combinations of orbital, vertical, and radial epicyclic motions near the innermost orbit. Those motions depend on spin, and so the frequencies become test lines drawn on a plot of mass and rotation. In supermassive systems, the analogous frequencies fall to timescales of hours and days, and hints of repeating patterns near these times have begun to appear in long light curves, especially in polarized infrared flashes from the center of the Milky Way. He observes another byproduct of the rotating frame, the way a fast spinner can lend energy to the fields that thread it. The classic extraction route in which magnetic lines anchored in the distant universe torque the horizon and draw out rotational energy turns spin into a fuel source that does not require accretion alone. This is consistent with jets that keep shining even when the thermal disk looks faint, and with the notion that some holes spin down over cosmic time, paying for their beams from their rotational savings account. He keeps an eye on the counterpoint because not all spinning holes launch mighty jets. The presence or absence of strong beams speaks to the available magnetic flux, to the thickness of the inner flow, and to the alignment or misalignment between spin and inflow. A thin, radiatively efficient disk may not carry enough vertical field to build a large reservoir at the horizon, while a thick, hot, low radiative flow can ferry field inward more effectively. Thus, the same spin can produce different outcomes depending on the state of the disk, and state changes can switch a jet on or off without a change in the underlying rotation. He looks for tests that might show cracks in the model. If the shadow ring size measured by very long baseline interferometry were to vary with viewing direction more than predicted, it could hint that the quadrupole moment of the object deviates from the expected relation with mass and spin. If the iron line profile could not be reconciled across independent instruments with a single inner radius, it could hint that geometry or gravity is not as simple as assumed. If a persistent echo appeared in the ring down of a merger, it could hint that the horizon is not a perfect one-way surface. For now the checks hold within uncertainties, yet the very ability to pose such conditional test is a triumph of the rotation story. He returns to the feeling that terror here is precision. Spin dictates where orbits end. Spin dictates how time flows in the inner rings. Spin dictates whether energy leaves as light as wind or as a pair of spears that cross a cluster. In this regime, preference becomes law. Gas that arrives must either align, tear, or precess. Photons that depart must follow bent paths that favour the approaching side of the disk. Particles that try to rest must learn to rotate. The stage itself turns, and everything upon it must answer. He steps from this rotating brink toward the shadows themselves to ask what lies beyond the horizon, and what the outer signs might reveal about interiors that no light can visit, where the next layer of the story balances known structure against carefully fenced conjecture. He studies the shadow and its subtle variations because at the brink where light almost fails, tiny differences speak loudly about gravity. A shadow around a black hole is not a substance. It is a silhouette traced by orbits that no longer exist, a negative space bounded by photon paths that skim the threshold and then escape. Around that darkness, a bright ring forms where bent trajectories and hot plasma gather. He focuses on three kinds of evidence that this rim can give with precision size that sets a strict ruler for mass and geometry flicker, that reveals motion near the last orbit and polarization that sketches the hidden order of magnetic fields. Size comes first because it is simplest and hardest to fake. For a given mass and distance, a theory with a standard rotating solution predicts a ring diameter set by where photon paths stack up. The first resolved rings match that expectation within tens of %, a strong vote for the usual gravity near the horizon. Yet even a small systematic offset persisting across seasons and instruments would hint at a different quadrupole moment than the standard family allows, and therefore at a breach in the rule that mass and spin alone set the external shape. He therefore treats every millimetre of angular size as an argument, and checks it against independent mass estimates from stellar orbits in the Milky Way, and from gas dynamics in distant giants. He notes that the ring is not the horizon. It is a photosphere set by where the plasma becomes transparent. Changes in electron temperature, density, and magnetic pressure widen or thin the glow, and scattering in the interstellar medium can blur or subtly shift the apparent edge. To reach a clean measure, observers compare multiple days' separate stable structure from weather, and use closure quantities that survive the moods of single dishes. What survives those filters becomes the trustworthy circle on which to test gravity. Flicker comes next and carries a different honesty, the honesty of time. In the centre of the Milky Way, the inner orbits complete in minutes, so brightness patterns can move across the ring at a pace a human can watch. Infrared flares from hotspots whirl, with periods of tens of minutes that match orbits near the last stable ring, and polarization angles swing as the knot goes around a dance that turns time into a tape measure for the curved stage. At millimetre wavelength, short snapshots freeze parts of that motion. When stitched together, they promise movies where arcs brighten on the approaching side and dim on the receding side exactly as special relativity demands. If a pattern appears to move faster than allowed, or if it fades in a way that contradicts the expected Doppler imprint attention, turns to geometry, to lensing substructure, or to a mistake that will teach something better. Over many nights, the statistics of flicker become a fingerprint of the inner flow. A spectrum of power that breaks at a time tied to the innermost orbit is a quiet vote for the predicted radius, and therefore for a specific spin. A lack of such a break persisting across frequencies would challenge assumptions about where the relevant emission forms. Polarization is the third key and often the most revealing because it encodes direction and order that total intensity hides. Polarized maps of the ring in a distant giant show lines that curl and cross in patterns consistent with a strong organized magnetic field near the hole, the kind of field that can launch and collimate a jet. The degree of polarization, its rotation with wavelength, and its variation with time together constrain the electron density, temperature, and accretion rate in the inner region. If the rotation of the polarization angle across frequency is large, Faraday effects are strong, and the gas is thick with low-energy electrons. If it is small, the inner flow is more tenuous or hotter. These measurements set upper and lower bounds on how much matter falls inward each second, and they do so without peering through the obscuring dust and starlight that complicate other bands. He considers what could mimic or mask these signals. Plasma can refract and scatter light in ways that impose their own structure, especially along the path to the galactic center, where screens of turbulent electrons reside. Weather in the flow can create asymmetries that look at first like a violation of symmetry in the metric. Flares can bias reconstructions toward crescents that wander. He watches the field address these traps with redundancy, different frequencies, different baselines, independent imaging pipelines, forward modeling that begins with the equations of magnetized flow and produces synthetic data to test against reality. Where all paths meet, trust grows. He thinks about substructure that standard images cannot yet reveal the higher-order photon rings that arise when light loops the hole several times before escape. Those rings are faint and sharp, stacked like whispers inside the main glow. If they can be separated with longer baselines or with instruments in space, they will provide a geometric target largely independent of plasma details a ruler made of pure lensing. A space antenna paired with Earth dishes would push to shorter baselines projected against the sky and peel away that delicate structure. He imagines a future map where rings of second and third order appear as knife-edge circles that fix mass and spin with a precision far better than any present technique, and where any tiny systematic departure from circularity becomes a test of whether the solution for a rotating black hole truly holds in nature. He weighs alternatives that would paint the shadow differently. A compact object without a horizon could allow some light to reflect from a surface filling the darkness, with a dim glow that varies with viewing angle and time delay. A condensate without a standard event horizon might imprint echoes in time, weak repeats of flares that bounced from an inner boundary. A star made of field rather than matter might lack a stable photon ring altogether, or might place it at an odd radius. Charge would alter the shape, but realistic environments drain charge quickly, so persistent charge is unlikely. None of these conjectures is promoted to truth. Each is a control case that must fail before confidence in the standard picture deepens. He brings the conversation back to instruments because precision requires partnership with hardware. The present network at 1 millimeter already turned Earth into a lens. The next generation will add dishes, widen the bandwidth and extend to shorter wavelengths, where the plasma is more transparent and the ring is sharper. Arrays in the infrared see hotspots dance at the same scales and provide a parallel record of motion. X-ray timing brings notice when the inner engine snaps, allowing coordinated campaigns that catch the same disturbance in several bands. The goal is not a pretty picture, but a set of cross-checked numbers ring diameter as a function of frequency and time polarization maps that track magnetic order-light curves that carry the rhythm of orbits. He looks for the smallest deviations that can carry the largest meaning. A persistent offset in ring size between two viewing angles could signal an unexpected shape of the mass distribution. A slow precession of the bright crescent could carry the period of a tilted inner flow locked to the dragging frame. A long-lived twist in polarization vectors that cannot be modeled by any reasonable flow could point to physics beyond the standard laws, or to a field configuration that current simulations have not yet imagined. He ends where terror takes the quiet form of a circle that ought to be perfect. The ring is a demand from gravity written in light. It leaves little room for invention. Either the numbers close or they do not. If they close, the certainty deepens until the shadow becomes a laboratory where every small turn of brightness and angle teaches the properties of matter, close to the threshold. If they do not, the failure will be precise and repeatable, and the revision to our picture will be forced by a line that refuses to move. In that sense, the most terrifying black holes are not the loudest ones, but the exact ones, the ones whose silhouettes do not blink, the ones that turn imagination into arithmetic at the edge of night. He steps past the rim and lets the mind enter where instruments cannot go careful to mark the line between what the sky demands and what thought permits. The exterior is disciplined by observation images of rings, spectra from hot iron waves from unions that ring down into silence. The interior is not visible, but it is not free. It must respect what the exterior shows, and it must solve problems that light and waves alone cannot settle. He begins with the oldest riddle, the fate of information. A black hole that evaporates by slow quantum emission seems to erase the particular state of what fell in, and erasure offends the unitary bookkeeping of quantum mechanics. Over decades, a path has formed where the outward radiation, when all of it is considered with its tangled correlations, can carry the record in an exquisitely scrambled form. Calculations of entanglement growth sketch a curve that rises and then falls, a page-shaped arc that returns information late, not soon. If that is the rule, the interior must be a theatre where scrambling is fast and complete, so that the exterior radiation can encode the story without contradiction. He holds alongside this the firewall paradox, a claim that preserving distant entanglement may force a violent surface at the horizon, ruining the gentle fall promised by classical gravity. He does not promote a wall of flame. He lists it as a caution that something must give either the exact pattern of entanglement, or the experience of an unremarkable crossing, or the locality of quantum fields near the boundary. Each concession reshapes the interior. He surveys proposed repairs and asks how they touch the outside. Soft hair that carries quantum numbers upon the horizon would alter subtle correlations in the outgoing quanta, leaving a trace too delicate for present instruments, but not beyond imagination. Wormhole-like dictionaries between entanglement and geometry would make the interior a network of connected regions, and though no portal admits travel, the mathematical relation could tame the contradiction. A bounce at the core, a Planck-dense star that resists full collapse, would shorten or prevent true horizons, and might return matter late in a faint flash. Exotic compact objects that mimic the exterior geometry nearly perfectly, but replace the horizon with a surface, would reflect part of an inward disturbance and produce late echoes in the waves after a merger. The laser interferometer, gravitational wave observatory, and its partners have searched for such echoes, and found none that survive severe tests, a result that does not prove absence, but does bind the loudest versions of reflection. The Event Horizon Telescope has mapped the polarized ring around a famous jet, and seen order consistent with the horizon threaded by field lines, rather than a luminous surface, yet even that image cannot rule out all substitutes that hide well. He watches how each interior story is forced to meet three exterior facts. First, the multipole moments of rotating black holes measured by future wave spectroscopy must match the simple formula that the classic rotating solution dictates, unless the object is not a black hole at all. Second, the tidal deformability during a near merger must be so small as to be effectively zero, because horizons refuse to bulge in the way normal stars do. Any measurable love number would point away from a true hole. Third, the shadow diameter must track the mass and spin in the clean way that the standard geometry lays out. Deviations beyond small allowances would challenge the exterior, and thus the interior as well. He leans on these facts and allows speculation only where the tests have not yet reached. He imagines a horizon that is almost perfect but slightly leaky at the quantum scale, releasing a faint correlated drizzle of energy that carries information without any outward spectacle beyond the slow aging of the whole. He imagines a core that never forms a singular point in the strict mathematical sense, because quantum geometry resists infinite compression, turning the trajectory inward into a long tunnel, where time dilates so extremely that an outside observer never sees the resolution. He sets against these pictures the quiet power of no-hair theorems, which tell that from the outside only mass, spin and charge matter, and he recalls that charge drains quickly in astrophysical plasmas, leaving only mass and spin to tell. Every additional interior degree of freedom must either remain perfectly hidden or learn to announce itself at a discernible level. He asks where to listen next. Gravitational wave spectroscopy of ring-down modes remains the sharpest ear. If future networks resolve 2 or 3 overtones with high precision, they can check whether each pitch and decay line up with a single mass and spin. Any systematic discrepancy would be a map to the interior. Extreme mass ratio inspirals in the band of a space-based interferometer will act as slow pens that trace the geometry just outside the horizon, sampling many radii and latitudes over months. Their precession rates and harmonic content will build a multipole portrait. If that portrait departs from the classic pattern, by even a little interior variation must be blamed. Another arena is the timing of hotspots near the shadow. If a long-lived mode persists at a period not permitted by any stable orbit, an unseen reflecting surface or a trapped fluid layer would be implicated. He watches tidal disruptions with a similar eye. If a black hole had a surface matter that slips below, the would-be horizon might strike and shock, producing a brief hard flash before being swallowed. The absence of such signatures in well-observed events, together with the success of models that rely on horizons, tilts the scale toward the standard picture, though not decisively. He weighs speculative claims of faint precursors or late flares as markers of partial reflection with caution, because geometry and reprocessing at large radii can imitate many things. He returns to evaporation and admits that for astrophysical holes, the time to fade by quantum radiation dwarfs any practical window. The central giant in the Milky Way would take a time far beyond the age of the universe to evaporate, and supermassive holes are effectively eternal on human and galactic scales. For that reason, tests of evaporation-based solutions to the information puzzle reduce to logic rather than observation. Logic itself can move mountains, but the mountains in this field are melted most quickly by evidence. He looks at primordial black holes, ancient relics that could have formed from density peaks near the earliest moments. If any such population exists with masses small enough to evaporate within cosmic time, their final flares would spray gamma rays. Constraints from space-based telescopes already suppress the number of such relics. If a heavier primordial population exists, its gravitational fingerprints in lensing and in cosmic structure are under active search. Discovery would complicate the narrative of interiors because the birth conditions would be unlike any stellar collapse, and evaporation could be tested in a range of masses. He keeps his language lean because the interior deserves humility. A singularity at the center is a statement of breakdown, not a material object. A firewall is a warning label, not a prediction. A wormhole is a dictionary entry, not a bridge to another place. Still, discipline does not forbid wonder. The power of the exterior tests is that they corner conjecture until only a few corridors remain. If those corridors survive ever sharper waves and ever clearer rings, they will earn promotion from conjecture to architecture. He ends by naming the fear that this layer summons. It is the fear that reality could be stranger than any controlled picture, yet remain so consistent at the surface that only years of patient listening will reveal it. It is the fear that the place beyond the horizon is both utterly alien and utterly constrained, a paradox that demands both imagination and restraint. He accepts that demand and turns to the fates of the giants themselves, to the endgames written in the mergers of galaxies and in the slow exchanges of angular momentum that decide how many horizons become one and how their rule deepens. He turns to the futures written for giants and watches how galaxies draw together and force their central rulers into uneasy partnerships that end in one horizon. The choreography begins at distances of hundreds of thousands of light years, when two star cities fall toward one another along filaments of dark matter. Tides pull out streams, disks tilt, and bars grow that drive cold gas toward each nucleus. As the halos interpenetrate each central black hole, rides within a cage of stars, and dark matter and dynamical friction tugs on those cages, bleeding orbital energy into the swarm and shrinking the separation from tens of kiloparsecs to a few. When the distance falls to of order 1 kiloparsec, the pair becomes a dual core, each still surrounded by its own stellar and gaseous neighborhood, sometimes both active at once so that telescopes see 2 points of fury inside a single distorted host. He follows the tightening further to hundreds of parsecs, where stars begin to feel the combined potential to tens of parsecs, where the pair binds into a gravitational binary, and to the classical worry called the final parsec problem, the fear that the supply of lost cone stars that can carry energy away will run thin before gravitational waves can do the rest. He watches nature supply solutions. Triaxial shapes in the stellar distribution keep new orbits wandering into the lost cone. Gas-rich encounters build a circumbinary disk that torques the pair and robs angular momentum efficiently. 3 body exchanges in crowded nuclei can sometimes add a third intruder whose chaos shortens the clock. In each case, the pathway narrows until gravitational radiation takes the lead, and the inspiral accelerates with a soft, relentless song. He sees the fingerprints of these stages in real skies. The Hubble Space Telescope and the James Webb Space Telescope resolve double nuclei in merging galaxies some, with dust lanes that spiral inward like braided rivers. The Atacama Large Millimeter Array maps cold gas in rings and streams that feed a shared disk, and the pattern of velocities shows cavities and overdensities where the binary's torques have sculpted the flow. The Chandra X-ray Observatory isolates hot points in the distorted core that betray accretion onto both partners, and long baseline radio arrays catch twin jets that tip the hand of a double engine. On larger scales, pulsar timing arrays report a hum at nanohertz frequencies, consistent with an ocean of supermassive binaries drifting toward union, a background that measures how often galaxies meet and how quickly their cores lose energy. He listens for rarer soloists within this background, the loud, slowly drifting tones of individual heavy pairs in late approach, and he imagines the future when a space triangle of laser arms hears those tones and alerts telescopes that a major collision will occur within a season. He traces the endgame to its consequences for the host. As the binary hardens, it scatters stars that pass within a few times, the separation flinging them to larger radii and carving a low-density core. This scouring can explain why the brightest ellipticals possess shallow central light profiles, why their hearts look chord rather than cuspy. The mass-ejected scales with the mass of the pair, so the largest giants create the widest hollows, leaving fossils that remember how many black holes have merged inside. Gas responds differently. A circumbinary disk can break into streams that flow onto each component near pericenter lighting, both in a periodic way so that the nucleus blinks with a cadence tied to the orbit. When the torque is strong, gaps open, and a lopsided ring forms that processes slowly imprinting another rhythm. Observers now search for these signs for quasars whose light curves show gentle clock-like modulations over years, for broad emission lines that slowly slide in velocity, as if responding to a moving source for narrow line regions that split into twins. Each candidate carries caveats because disks can flicker for other reasons, and winds can shift lines without orbital cause. Yet a few systems persist as credible binaries on subparsec scales, their signals steady, and their geometry supported by multiple channels. He lingers near the moment of union and the kick that may follow. When horizons touch, the pattern of emitted waves is not perfectly symmetric, and the newborn black hole can receive a recoil of hundreds to thousands of kilometers per second. If the kick is modest, the remnant oscillates within the core and settles, leaving weak ripples in the central stars. If the kick is strong, the remnant can be displaced for millions of years, dragging its inner gas with it and lighting as an off-center active nucleus. In extreme, if the escape speed is low, the remnant can leave the galaxy entirely and wander the halo or the intergalactic medium as a naked engine, with a retinue of hypercompact stars bound to it. A handful of galaxies show promising signs of displacement emission lines offset from the host starlight cores, shifted from the photometric center, tidal wakes that point like arrows. None alone closes the case, but together they sketch a reality where even the heaviest anchors can be hurled by their own waves. He returns to the fate of spin in these mergers. The final spin depends on the masses and orientations of the parents. If gas has kept the inflow coherent for long times, the spins may align, and the remnant will rotate rapidly with its axis stable. If growth has been chaotic, the spins may cancel, partly leaving a slower remnant whose direction wanders. Each outcome sets the next era of feedback. A fast spinner threaded by strong magnetic flux can power a persistent jet that keeps a cluster core warm, while a slow spinner may glow in radiation without strong beams. Thus, the genealogy of spin written by past mergers is not a footnote. It is a policy for the future climate of the galaxy and its neighbors. He looks outward at the cluster scale where many mergers chain together. In the centers of galaxy clusters, jets inflate cavities in the hot medium, in a cycle of gentle violence that balances cooling for hundreds of millions of years. When two clusters merge, their central galaxies fight for primacy, and their central black holes may pass one another pair and merge with a delay set by the density of stars and gas. The pattern of cavities and ripples that Chandra maps in X-rays becomes a ledger of energy injections, with each bubble a receipt pinned to the time when the core last exhaled. He listens for the way mergers reset these cycles, sometimes turning a quiet caretaker into a storm, and sometimes quenching a jet by starving it of ordered magnetic flux. He weighs the endgames far back in time when the universe was young and galaxies small. Their mergers were more frequent and gas was more abundant, so the path from dual cores to tight binaries to final unions may have been faster. This would help explain why supermassive black holes with billions of suns appear early, because mergers both add mass and stir inflow that accelerates accretion. Yet he is careful because overdoing mergers would erase disks and overheat the population. The balance recorded in the demographics of galaxies today, with a mix of spirals and ellipticals, and a relation between bulge mass and black hole mass, implies that growth came by both steady feeding and by collision in proportions that vary with environment. He considers how the most terrifying endgames are not explosions, but adjustments that never stop. After a merger, the remnant sits in a core it helped carve, surrounded by a deficit of stars that will take eons to refill. Its spin has changed, its axis may have tipped, and its jet, if present, will redraw its channel through the halo. If the recoil has displaced it, gas will fall in along new paths, triggering bursts of star formation in unusual places, and the nucleus will leave a trail of ionized knots like beads along a scar. Every outcome leaves a memory in light, and in the distribution of matter and telescopes learn to read that memory with higher and higher fidelity. He ends this layer by returning to the waves that arbitrate the final step. Earth-based interferometers sing at high pitch of stellar scale unions, pulsar timing arrays, hum with the grand chorus of the heaviest pairs, and a future space triangle will bridge the middle. Together they will not only count how many endgames occur, they will weigh how they proceed, and they will test whether the ring down of the newborn horizon speaks in the exact notes that the classic rotating solution prescribes. If it does, the story of mergers will become a precision tool to measure how galaxies grow. If it does not, the discrepancies will not be vague. They will be numbers that refuse to fit, and those numbers will point straight at a revision of gravity itself. Terror here is inevitability. When galaxies meet horizons, do not negotiate. They spiral, they merge, they ring, and they write new rules for everything around them. He gathers the threads into an unfinished map, not a wall chart with borders and labels, but a living atlas whose pages write themselves as instruments, learn new alphabets of light and gravity. He stands at a vantage where the outer path from cosmic seeds to city rulers is clear in outline yet messy in detail, where the first flickers beyond the era of recombination hint at direct collapse in rare hot lagoons, while heavy stellar deaths leave their own compact airs, and where early quasars insist that some engines found a way to run fast before galaxies had time to settle. He adds the middle steps where bridges of thousands to hundreds of thousands of suns now show through fog in clusters that run collisions to completion in dwarf hosts with whispering cores, and in tidal flares whose temperatures and tempos demand a middleweight interrupter. He inks the districts of accretion where disks, coronas, winds, and jets share the work of turning falling matter into power, and where the Event Horizon telescope draws a ring that behaves as gravity prescribes, while the Chandra X-ray Observatory and the European missions fold iron light until it fits the shape of the last stable orbit. He writes the roads of escape where jets carve lines through halos and regulate the weather of clusters, and he writes the ferries of fate where gravitational waves carry mass and spin into a final union, ringing the newborn horizon with a music that has matched so far the notes predicted by the classic rotating solution. He shades the interior regions with crosshatch marking them as present, but uncertain a space where information may scramble and return in tangled radiation, where exotic substitutes for a horizon are constrained by echoes that are not heard, and by shadows that do not glow yet, where logic alone keeps some corridors open until finer ears and sharper eyes narrow them further. The atlas as it stands has anchors that feel like bedrock. The relation between bulge stars and central mass, though strained by outliers, persists as a statistical treaty that reveals feedback at work. The presence of jets as climate control in clusters explains why hot gas refuses to cool catastrophically. The growth of heavy stellar mass black holes in low metal environments and their unions heard by the Laser Interferometer Gravitational Wave Observatory explain why the mass spectrum extends into ranges once thought unlikely. The ring around the shadow in the Great Elliptical Galaxy and the more jittery ring in the Milky Way confirm that near-horizon geometry is not a metaphor but a measurable stage. Yet around every anchor are margins that invite revision. The fastest early growth pushes models toward supercritical inflow, toward beamed escape, or toward seeds born large, and the balance among those routes remains unsettled. The census of intermediate engines is still thin and tangled with impostors whose geometry can mimic mass. The reasons why some fast spinners launch mighty jets, while others do not remain tied to magnetic flux and disk state in ways that need more movies at the ring and more polarization maps to decide. The catalogue of mergers hints at second-generation growth across the pair instability gap, but the fraction of such stair steps and the environments that favour them need years of additional waves to quantify. He draws the instruments on the margins like compass roses because they set direction. The James Webb Space Telescope resolves red compact cores in the young cosmos, where stars alone cannot account for the power, and it dates bursts of star formation around suspected seeds. The Atacama Large Millimeter Array watches cold gas spiral inward and outward, a record of feeding and cleansing written in carbon monoxide lines, and dust continua. The Neil Gehrels Swift Observatory and ground surveys discover flares quickly enough for the Chandra X-ray Observatory, the XMM Newton mission, and the Nuclear Spectroscopic Telescope Array to pounce building full spectra that tell whether a fresh disk has formed or a wind has turned hard light into soft. Pulsar timing arrays already sense a slow rise that smells like supermassive pairs, and the planned triangle of spacecraft will open the band where those pairs sing alone, offering months of warning and precision that turns merger stories into calibrated tools. He writes in the techniques that elevate seeing into knowing. Very long baseline interferometry makes Earth into a lens, but closure quantities that survive weather make it a trustworthy one. Reverberation mapping turns time into distance and distance into mass. Polarization rotates not only with wavelength, but with meaning tracing where electrons are hot, where magnetic threads are taut, and where flows are thick or thin. Power spectra of flicker define breakpoints that draw rulers near the innermost orbit. Joint campaigns invert puzzles by insisting that one disturbance must leave consistent signatures from radio to gamma rays, and that failures to link bands are as telling as successes. He marks the errors that keep the map honest. Scattering screens to the galactic center can smear fine structure, and must be modelled with independent probes of turbulence. Beaming can inflate power, and must be corrected with geometry that radio very long baseline maps reveal. Selection effects that prefer bright states can bias demographics, and only patient survey-grade watching restores balance. He keeps a ledger of wagers that the next decade invites. He expects the ring to become a movie, and higher-order photon circles to emerge as knives within the glow, a plasma-independent ruler that pins mass and spin with far tighter error. He expects extreme mass ratio in spirals to trace the multipoles of space-time outside real horizons, checking whether mass and spin alone suffice. He expects dozens of off-center tidal disruptions to sharpen evidence for middleweights, and a few convincing recoils that prove newborn giants can be shoved by their own waves. He expects that neutrinos will be tied firmly to at least one Blazar-class flare, and that the hadronic fraction in some jets will cease to be guessed and begin to be measured. He writes in fainter ink speculations that will either fade or darken. Perhaps some early engines are primordial and skip the story of stars leaving fingerprints in lensing statistics, and in the abundance of small hosts with oversized cores. Perhaps a dark sector with weak self-interactions nudges gas toward collapse in certain ancient fields. Perhaps small controlled deviations from the expected ring-down appear, when signals are stacked not as showstoppers, but as nudges that point to corrections in the quantum dressing of horizons. He ends the atlas not with a legend, but with an orientation. Terror in this map is not a scream, but a straight line, a ring that refuses to budge, a light curve that beats with the law, a wave that sings the exact pitch, The dread comes from the strictness of a cosmos that lets a boundary exist, where escape loses meaning, and then forces that boundary to decide the fate of cities of stars. The wonder comes from the way the same rules turn catastrophe into measurement. A star shredded becomes a yardstick. A jet carving a lobe becomes a thermostat. A merger that rings becomes a spectrograph for geometry. He closes the atlas for now, knowing that it will reopen with new pages, and he turns to a soft coda that lets the mind drift, while the rules keep working a wind down where the sky's hardest engines become the quietest escort to sleep.